Okay, so in this clip, we're going to take a specific example this time. We're not going to make it any more complicated than in the previous one where we did just a generic nucleophilic addition. But in this one, we'll take a specific example. Again, we'll take the ethanol starting molecule, and it's relatively simple in its starting point, and we'll react it with the Cn- ion. This is a common reagent. It's good for introducing carbons into a carbon chain, but also then once you've got the nitrogen in there, you can go down amines and amino type reagents and reactivity syntheses as well. So the lone pair of electrons attacks the carbon delta positive. That then bounces out the electrons onto the delta minus oxygen there. And what that then does is opens up the molecule to create the O- there, which is now attached to the nitrile with our hydrogen and our methyl group. This can then, as in the previous generic example, picks up a proton from somewhere, and this then creates the product, which is your 2-hydroxy propanitrile molecule. Now this is a nice molecule because it's one of the first examples of a chiral molecule, and what that means is that the central carbon is connected to 4 groups, each of which are different, so that none of those groups are identical. And what that does is it makes this central carbon chiral. And in a subsequent clip, what we'll do is we'll draw these molecules side by side to show how that chirality exists in 3-dimensional space, because it's now possible to rearrange these groups, not to change the connectivity, so each of these 4 groups will still be attached to this central carbon, but their 3-dimensional orientations will now be different. And this all comes from this very first initial attack of the nitrile Cn- ion into that initial carbonyl bond. That initial attack, whether or not it's from above the plane or below the plane, again we'll look at that in more detail in a subsequent clip, but that first initial attack defines the chirality of the molecule and allows it to form one of 2 optical isomers. Okay, so where they've got the same molecular formula, but this time they've got a different 3-dimensional arrangement in space around that central carbon there. Okay, so we'll go on to the next clip and we'll show you how these things look in 3-dimensional space.